Hi, my name is Scott Simpson, and today what we're going to be doing is we're going to be plugging this force constant in. We derived a value for it. We're going to be plugging it into our Schrodinger equation, and then we're hopefully going to make this look more like a differential equation, come up with some solutions, and come up with some plausible wave functions that could be utilized in a quantum harmonic oscillator. So again, what we're trying to do is we're trying to take this and plug in this value, which we just figured out. So let's hop back to our applied Schrodinger equation. All of that applied to x, psi x. I think it just glitched out there for a second. And we're going to plug in that k. So before we do that, though, we're going to apply this differential. So we're going to get our wave function in here. We'll have our wave function connected to here, and then we'll plug in for k. So if we apply our wave function, what I'm going to do here is just distribute this wave function or have the operators act upon it. 1/2 4 pi squared, the frequency squared, m x squared is then equal to e I, which depends on x. Here we can see that this will end up canceling out to be a 2, and we'll leave it that way. So when everything's cleaned up, we get the following expression for our Schrodinger equation. Okay. However, this looks tough to think up of a solution for. Whenever you consider differential equations, you're trying to look at an equation and say, all right, I can solve this equation without knowing the function, so I'm going to have to guess some functions. It's pretty tough to do that when it looks like this. The easiest route I find is to get one side equal to 0. And once you do that, you might be able to think of some functions that could work out, or you could apply different methods that you learn in your differential equation class to solve for this thing. So this looks tough to solve. Let's make it easier. Okay, so to do that, what we want to first do is isolate the toughest part. I think this portion over here is the toughest part. Second derivatives can be difficult to deal with, more so than just having a function hang out. So let's get this thing by itself, meaning we're going to have to move this away from this term. So let's multiply negative 2m h bar squared. So we're going to multiply this thing. Sorry, trying to get this board to move that tissue box out of the way. Okay. So when we do that, that term's going to go, that term's going to go away. We're going to be left over with this, but we have to multiply everything else in this expression by that negative 2m over h bar squared. So multiplying negative 2m over h bar squared on this thing, that's going to change this to negative 4 pi squared v squared. We have another mass that gets tacked in here, so we got m squared all over h bar times x squared psi of x. And then we have to multiply this e by that term too. So we end up getting negative 2m h bar psi of x. Okay. So I said it's easiest if we can get one side equal to 0. I suggest we move this over to the other side because then we can isolate it. This side will become 0. So when we do that, x squared psi of x, this becomes a positive. So we're at 2m h bar squared psi of x is all equal to 0. Let's rearrange this because there's a lot of messy stuff in here. And I would just sort of like to simplify and get similar terms squished together. So it'll make it easier to think up of solutions. So if we rearrange this, what you can get this to work out to be, we can pull some terms out, rearrange, and then we're also going to define, this stuff is just a collection of constants. It's annoying to deal with. So how about we set a new term alpha is equal to 2 pi bm h bar. You might be asking, well, why don't we just set this whole thing equal to alpha? That way, we don't have to square alpha to get what we want. There is a reason for that. It would become clear in a little bit on why we're doing this. So for now, just trust me. I know that's a hard thing to do, but just trust me. So we get second derivative with respect to x. We get negative alpha squared x squared psi x plus 2me h bar psi x is equal to 0. We didn't actually rearrange or combine like terms. So what we're going to do next, we can pull out the wave function in this portion. To e h bar squared minus alpha squared x squared, all of that times psi x is equal to 0. Okay, so this is our differential equation that we have that we should be able to solve and figure out. There are a handful of possible solutions, but the one I'm going to suggest we use, and it's worked out in the past for many other people, is to assume that we have a Gaussian function. So for now, we're just going to say, let's assume we have a Gaussian function. I know it will work. How do people determine this? Well, from differential equations, they know that Gaussians work this way. We're going to have to whittle our way down to get to explaining why in a bit, but it will work. So let's assume solution for the wave function follows a Gaussian function that has the following form. So what we have here is, excuse me, an exponential where that alpha term, which we defined up here, shows up. It's divided by 2, x squared. And then we have this other function. This other function is a power series where we're going to define f of x is equal to power series where we have some constant, we'll call it c sub 0, plus constant number 1, x raised to the power of 1, plus c2, x raised to the power of 2, plus c3, x raised to the power of 3, plus blah, 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 blah. And it goes on for an infinite amount of time. We can truncate that at certain points, and we will eventually do that. But let's just see what happens. Okay. So now we have a trial wave function. We don't know if this actually works. So what are things that wave functions have to be? Well, we know from the postulates of quantum mechanics that wave functions must have a single value at any point, or at least in the range it's been normalized. We know that the wave function has to be continuous. A wave function is continuous. That also means its derivative and its second derivative must also be continuous. So since we have that requirement from the postulates of quantum mechanics for wave functions must be continuous. The first derivative and second derivative must also be continuous. Okay, so this is where we're going to have to do some differentiating. We're going to have to utilize the chain rule quite a bit and the product. So if you don't remember how to do those, especially for exponential functions, I highly suggest to go back, review some calculus, and see how that's done. Of course, I'm going to walk you through the steps so you can see how it is done, and you can check it over, but it would be a good idea to really know how to do it. Okay, so let's consider the first derivative of our function that we have. So let's consider the first derivative. Okay, so this is our function. We have to just take the differential of this guy. So let's do that. Equal d dx of e minus alpha x squared over 2 times f of x. And we'll worry about when we start differentiating that thing, that power series, what that looks like. For now, we're just going to call it f prime when we take a differential. Okay, so we have two functions that depend on x that are being differentiated. We have to apply the product rule, and then within that, we also have a chain rule for this function here. So product rule, derivative of the first times the second. So we got to take the derivative of this guy. We utilize the chain rule. And we find that this is the differential of the first function times the second function. Plus, now we got to take the first function and then we multiply the derivative of the second. So that's what the first derivative would look like of our wave function, assuming we have that Gaussian function. And again, we'll get back to what these things are. For now, it's just nice and neat to keep it this way because we're going to find there's some cancellations out. Okay, so we did the first derivative. That one's easy. Looking at this thing, you can guess the second derivative is a little more ugly. So let's consider the second derivative. So we already took the first derivative up here. So let's do it again. D dx of negative alpha x e to the negative alpha x squared over 2 times f of x plus e negative alpha x squared over 2 f prime of x. Okay, again, this time we have two product rules, and then we have to apply the chain rule in a couple different spots to make this work out. Okay, so let's do this. So we got to take the derivative of the first function times the second. And then we'll take, so of this first term, and then we'll start applying it to the second one. Okay, so let's take a derivative of this guy then. Let's see what we get. In that case, we should get, we're going to pull out a negative alpha again. So we get negative alpha x, or alpha squared x squared minus alpha e to the negative alpha x squared over 2, because we have a chain rule that's in all of this, times f of x. Then we have second part. So we got negative alpha x e to the minus alpha x over 2 times first derivative of x. We'll leave that alone as is. Then we have this other term that we're going to worry about, plus negative alpha x e to the negative alpha x squared over 2 f prime of x plus e to the minus x squared over 2 f double prime of x. Ugh, that looks ugly. Well, if you rearrange this thing around and you do some massaging, you can pull out an e to the alpha x squared over 2 out of some of these functions and kind of leave everything else alone. And what you should see is we get x, f of x. So that's for that first term with f of x applied. Then we have minus alpha f of x. Then let's look at this other portion. We pulled that guy out, so we should get negative alpha x times f prime of x. Pulled this guy out, so then we should just get, let's see, another minus alpha x f prime of x. And then finally, at the end of this thing, f double prime x. Okay, so it looks a tiny bit better, but there are certain terms that we can squeeze together. So we have two double primes here, or excuse me, we have two single primes or two first derivatives of these power series. Let's slap that together. And what we're going to do is we're going to have terms that only rely on f of x in one portion, and then f double prime, or f single prime and f double prime. We could combine these two, but I'm going to leave them alone for now for reasons that we'll hopefully see in a little bit. X squared f of x minus alpha f of x. Combine these, so that will become just negative 2 alpha x. Whoops, don't need to put a square there. Plus f double prime of x. Okay. So now, does this actually look any better? Not really. What we're going to do now is we're going to take these derivatives that we've developed, and we're going to plug them in to where we need to into the Schrodinger equation, and we're going to see what comes out. So if you remember, so we want to sub into our Schrodinger equation, where basically we have f double prime of x plus 2me h bar squared. Let me make sure that was an h bar squared. Yeah, we're good. Minus alpha x squared psi of x is all equal to 0. So remember, we came up with expressions for this. So let's plug this big thing in there. We get e negative alpha x squared over 2 alpha x squared f of x minus alpha f of x minus 2 alpha x f prime of x plus f double prime of x. That was just this thing that we put in here. So sorry if your hand's cramping at this point. And then we'll bring down these two other portions. So what we're going to do at that point is, again, we know that this guy, we assumed it looks like the function negative alpha x squared over 2 times f of x. We're going to plug that in and see what we get. So we get plus 2me h bar squared minus alpha x squared times e to the minus alpha x squared over 2 f of x. And that is all equal to 0. I can barely fit that on the page. I am so sorry. Okay, what we're going to do next is we're going to distribute this through, and we're going to see if anything cancels out at certain points. So let's do that. The interesting thing is everything is multiplied by this e to the minus alpha x squared over 2. So what we can do is we can just pull that out. We can divide that through, and since the one side is 0, that gets removed, which is nice. And we're left over with following after we distribute this f of x through. Double prime of x. And we got plus 2me h bar f of x minus 2 alpha or x or alpha squared x squared f of x is equal to 0. Okay, so let's try and find some things that will either cancel out or knock each other out. If you were wondering why did I leave that thing alone, well, hopefully you can see it right now. If you look, that guy gets canceled out by this one. And with that, we're left over with the following expression. I'm going to rearrange this a little bit, but note that these two things cancel out. Let's put f double prime out in front, and then we'll have the single prime terms together so we can find those. We only have that guy that's a single prime. So we get 2 alpha x f of x. So we've gotten that one. Let's keep track of the ones we're taking care of. We've gotten that guy out, that guy out. Now we just need to combine these two. And since they both have f of x in there, we get 2me h bar squared minus alpha all times that f x is equal to 0. Whew, that was a lot of work to get to another difficult equation to solve. However, we can solve it. So what we are going to do next time is we're going to actually look at putting in the power series for here. But what we have to do is we have to make sure they have matching indices or indexes when we are trying to utilize them in the same equation. So with that, I'd like to thank you. Just keep in mind that next time we'll be plugging things in.